Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some calculus end-of-the-year exam preparation. We'd like to thank everyone that's joining us tonight for the first time. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm super excited to be joined tonight by our three panelists, Steve Kokoska, Tom Dick, and Vicki Carter. Tom is a senior math advisor for Texas Instruments and is also professor and former chair of the math department of Oregon State University. He has served on the editorial panels for the Journal of Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's AP Calculus program and has previously served as chair of the AP Calculus Test Development Committee. He was inducted by the Oregon Council of Teachers of Mathematics in the Oregon Mathematics Education Hall of Fame in 2008. Tom, thanks so much for joining us tonight.
Oh, it's great to be here. Thanks, Mike.
And Vicki has been teaching high school math for 41 years and currently serves as the math department chairperson at West Florence High School. She's a former co-chair of the AP Calculus Test Development Committee and served as exam leader at the AP Calculus reading in the summer of 2017. She received the T-Cube Leadership Award in 2015, and Vicki has served on TI-Nspire authoring teams and has presented at many international, national, and regional conferences in the areas of technology, calculus, and statistics. Vicki, so great to have you with us tonight.
Yes, it's a pleasure to be here.
And last but not least, Steve is a professor in the Department of Mathematical and Digital Sciences at Bloomsburg University. He just completed his term as chief reader for the AP Calculus reading and as a member of the development committee. Steve's an active T-Cube instructor and College Board consultant with recent workshops in China and Singapore, and he just published an AP Calculus textbook. Steve, we're really excited to have you with us tonight.
Thank you very much, Michael. Very happy to be part of this presentation.
Tonight we're expecting a large crowd, so your audio is automatically muted. Feel free at any time, if you have any questions for Steve or Tom or Vicki, to use the Q&A window on the right side of your screen. If you have any general questions, we might be using the chat window to send general messages. But any questions should be directed in the Q&A window, again, to Steve, Tom, Vicki, or myself. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Also, we'll be providing a link for all the documents that are being used tonight. And although you may have a TI-84 or TI-Nspire handheld or software sitting in front of you, we found that the best way to experience the webinar tonight is just to kind of follow along, and then in a couple of days you'll automatically get an email with a link to the recording. And with that recording, you can really go along at your own pace, which is what we recommend. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. And if that doesn't resolve the problem, in the same window where your name is located in the participant window, you'll find a little icon that has a little phone icon. By clicking that phone icon, you'll automatically get call-in information, and you can switch from the audio broadcast, which is the default, to call in using a phone or a cell phone. At this point, Tom is going to discuss our agenda.
Okay, thanks, Mike. We've done the introductions. So what we're hoping to accomplish tonight with you all is to just go over some basic questions and answers regarding getting ready for the AP exam, reviewing the exam format, and especially a close look at what's to be expected on using your calculator. We'll get through some examples. We'll look at some do's and don'ts, especially with respect to technology. These are things that can help students save time on the exam so they can spend more time thinking about the calculus rather than wasting time, for example, re-entering things that they only need to enter once onto their calculator. As I said, we'll do that through an example. We picked something that's a really common, shows up on most years on AP exam, is some problem having to do with area and volume. And that's a great one to kind of illustrate some of these do's and don'ts. And finally, we'll say a little bit about some new video resources that Texas Instruments has recently made available on their education website, and talk about what's available there on the TI in Focus. All right, let me hand it back
Tom.
to Mike.
I was going to say, Tom, thanks so much. Steve, you have control. Feel free to share your screen.
Oops. Okay, let's see if we can do this. Let's see if I can work this. All right. How about that, Michael? Visible?
It looks great, Steve. Thanks so much.
Okay. Excellent. Very good. Okay, so thanks, Mike. What I've tried to do here over the past couple of years is to create a collection of what I call frequently asked questions and some answers. Questions that come to me from mostly AP Calculus teachers, but some from students. Excuse me. And what I've done tonight is I've taken a look at a lot of those questions that I've compiled, and I've weeded out the test preparation questions and answers. So I'm going to go through a couple of those as we get close to the exam, and hopefully provide a couple of extra tips that'll get your students some extra points. So here we go. One of the most common questions I get these days has to do with sign charts, and I get a question or two like this. It says, are sign charts required to be labeled? And maybe more importantly, are they accepted for justification on the free response portion of the exam? Excuse me, here's my answer to that. Look, a sign chart, in my opinion, is a wonderful mathematical tool. Mathematics has some great notation and great language, and I still believe, and I still use sign charts in my class. However, on the AP Calculus exam, a sign chart alone is not acceptable justification, say, for example, for local extrema or for inflection points. So students can certainly use a sign chart, and I would encourage them to do so. But they need to supplement that information with some sort of calculus statement. So what I mean by that, or I'm going to illustrate that with an example. Let's suppose that the function f has a relative maximum at x equal a, and a student is exploring this and has discovered that, let's say, by using a sign chart. They need to support that with a calculus statement, and here are some possible statements or justifications that they might use. One of the most common and easily accepted statements is f prime of x is positive to the left of x equal a and negative to the right of x equal a. Another one, a little bit more succinct, is f prime changes from positive to negative at x equal a. And finally, down at the bottom of this screen, a student might say that f prime of x is greater than 0 for x less than a, and f prime of x is less than 0 for x greater than a. Now, I've added a little bit here in parentheses because there is a question, if a student writes this, there is a question about whether they're making a local or a global argument. For example, are they saying that f prime of x is greater than or equal to 0 for all x less than or equal to a? Or are they really talking about just a little region, a small interval, just to the left of a? So, although they can probably get away with that third statement for justification, depending upon what they're justifying, I would suggest that the first two are the best to use. And just to justify my statement here a little bit, it was absolutely delightful to see on the 2017 scoring guidelines a couple of sign charts. I don't think I've seen a sign chart on the free response scoring guidelines, and I don't go by years, I actually go by where we graded the exam. I don't think I've seen one since we were in Fort Collins. I could be wrong on that. But it's nice to see these two sign charts. And this visualization, these graphs were used to determine when both particles in this problem were moving in the same direction. So I would like to suggest that students can explore and discover how to answer this question, but they still need to include a calculus statement. And what I've outlined or highlighted here in yellow is typical of what they would have to say. And that is, since the two velocity functions have the same sign on those two intervals between 1 and 3 and 5 and 8. So here's another one. What are the key skills that I have to focus on or work with my students on the free response questions? I get this question frequently from AP Calculus teachers. Look, what should I focus on as the test is approaching? What key concepts should I look at? Here's my answer to that. And Michael, I apologize. I probably should have put number 4 first. Those of you who have been teaching AP Calculus are certainly familiar with the AP Calculus curriculum framework. And you know now that everything has a code. All of these learning objectives and essential knowledge statements all have certain codes. And when the exams are created, when they're constructed, all of the questions are coded by LOs and EKs. And you know that the Test Development Committee is very careful to make sure that they address all of the LOs and EKs, or OK, as many of them as they can. So no one particular learning objective or essential knowledge statement is targeted. Now, that said, this is what I think I have seen over the past few years. I certainly believe that there has been an emphasis on conceptual understanding. If you've been teaching AP Calculus for a while, and if you've been looking at the free response scoring guidelines, you'll notice that there have been some conceptual points over the last, let's say, 4 to 6 years, where students have demonstrated some sort of conceptual understanding on the way to solving a problem. My belief is that that will continue. It's not a large number of points, but I still believe that there is a focus on conceptual understanding. In my answer number 2 here, I also believe that there's been more of an emphasis in scoring the FRQs on notational fluency and especially communication. I think we're paying much more attention to using correct notation and communicating answers succinctly, precisely, without any extra information. And of course, in number 3, students still need to use technology, and they need to use it appropriately, and they need to communicate to us how they've used that technology. So my next question is, well, what are the most frequent errors that I've found while grading the AP Calculus exams? And what can we do as teachers to remind our students about these errors? How can we avoid them? Well, I'm glad you asked. I like this question. Here's a list of what I think are the most common student errors. Here's the first one. If f prime of x is equal to 0, that's true if and only if f of x is a relative maximum or a relative minimum. And of course, that isn't true. Places values of x where the first derivative is 0, along with places where the derivative doesn't exist, are candidates for extrema. And this kind of ties together with my first question for tonight. How would I determine whether or not they're an extrema? Well, I would explore by using a sign chart. And of course, you know what's coming here in question number 2, or common error number 2. F double prime of x is equal to 0 if and only if the point x, f of x, is an inflection point. That's a common error, and that, of course, is not true. Places where the second derivative is equal to 0 or does not exist are candidates for points of inflection. And once again, I would at least start to explore this by using a sign chart. Here's another common error that I've seen recently, and that is where students are asked to find the average rate of change of f over an interval a to b. I'm not sure if this is showing up well on the screen, but these two responses, these two expressions are in red. They're wrong, and they're two very common errors from students. The first one on the left there is where a student sort of takes the average of those two values, f of a and f of b, And the second common error is where they sort of take the average of the derivative of f at a and the derivative of f at b. And I didn't put the correct answer in here, but of course f of b minus f of a over b minus a. This is another common error, and I think Tom and Vicki might be talking about an area of volume problem that might involve this formula, where a student has to find a volume by using washers. And a very common error here is to write that integrand as the outer radius minus the inner radius, that quantity, that difference squared. And of course that's incorrect. And let me just remark that even if a student writes this, and let's suppose that this is a calculator active question, even if they produce the correct answer by using their calculator, they still will not receive full credit. They must write the correct mathematical expression as given on the right-hand side here. I have lots of common errors associated with separable differential equations. Look, if a student is given a differential equation and they're asked to solve it, separate the variables. That's the first thing they need to do. The only technique that we ask them to know about to solve a DE is separation of variables. So in my first line here, where I'm given the differential equation, I've shown a correct separation of variables. In the next line down, this is a very common error. What students are doing these days are separating the variables, but without regard to any algebraic operations. So some students are just taking, for example, if you can see that, y minus 3, and just placing it on the left-hand side without regard to dividing by y minus 3. So I'll just put all the y's on one side and all the x's on the other, and of course that's incorrect. I often get this question associated with differential equations, you know, where does that constant belong? Can I put it on the left with the, say, with the y's, or can I put it on the right with the x's? And the truth is, of course, it doesn't matter. It's most common to associate or put that constant plus c on the right with the x's, but we have lots of students in solving these problems put a C1 on one side and a C2 on the other, and that's okay, and then they combine them into one constant. In my next line down, I guess I maybe should have put this up above a little bit, but don't forget that plus C. Many students in solving these separable differential equations forget to include that constant C. And I'd like to suggest that in solving these problems, to use the initial condition before explicitly solving for y. And this is a little cryptic example, but this is what I mean. If you take a look at that expression at the bottom of this screen here, log of the absolute value of y minus 2, that starts out that way. Suppose that was the result of integrating on the left-hand side with respect to y and on the right-hand side with respect to x. From that line, I would now plug in my initial condition, my value of x and my value of y. I think for two reasons. Number one, it's a lot easier to do so at that point. And the second reason is if you go on and try to solve this for y, I think it's harder with that constant c in there rather than a specific number like 7 or 82. So use the initial condition at this point before solving explicitly for y. Here's another one. In particle motion problems, don't forget to use the initial condition. If you can see it on the screen, that x of 1 is in blue. Many students, some students, will forget to use that initial condition. I kind of think of this as an application of the fundamental theorem of calculus. And don't forget you need that x of 1 in here. That initial condition should agree with that lower bound on the definite integral. Use good communication skills. This sort of ties together with one of my earlier questions and answers. It's not really a good idea to respond or to justify an answer by saying, it increases then decreases. Well, what does a student mean by it? They probably should not say something like the function is positive to the left of 5 and negative to the right of 5. Which function? Are they talking about f? Are they talking about f prime? So they have to be very careful about what they're referring to here. In number 8, make sure to include the mathematical setup whenever you're using a calculator result. So, for example, in this particular problem, if the answer to the problem is minus 0.419, the student has to tell us where that came from. They have to tell us the mathematical setup in this particular problem, the definite integral. Just writing the correct answer is not sufficient. So in AP Calculus lingo, that would be called a bald answer, and bald answers rarely get full credit. So you have to write the correct mathematical setup. And down at the bottom, number 9 here, we see some of these errors. This is what I call universal logarithmic anti-differentiation. So some students who see an f of x in the denominator, regardless if the derivative of f is hanging around or not, will write an antiderivative here as the log of the absolute value of f of x. And of course, that's not correct. And unfortunately, I think in recent years, we've seen a number of, well, what I might call elementary chain rule errors. For example, just taking the derivative of e to the 4x, students will forget to take the derivative of the inner function, in this case, of that exponent. And in my second example, if a student goes to take the derivative of f of y with respect to x, they'll forget to take the derivative of that inner function y. In this case, they'll forget to multiply by dy dx. Another common error I've seen recently is that students who assume that absolute extreme values of a continuous function on a closed interval occur only at the interior points. I'd like to suggest that in solving these kinds of problems that students consider a table of values. And in considering that table of values, remind your students that they have to check at the endpoints of that closed interval. And finally, we've seen a lot of what we call linkage recently, and I think of this as a stream of consciousness. And I'll bet you all have students who do something like this. They solve problems in just sort of one continuous line, and they connect all of their statements with equal signs. And in grading the exam, students cannot connect expressions with equal signs that aren't equal. And here's a simple example. This is an average value problem. So let's suppose that a student reads a problem and they recognize, okay, I've got to find the average value of this function over the interval 2 to 5. And they start out by finding an antiderivative, and they evaluate that antiderivative at 5 and 2, and they find the difference, and they get 117 divided by 2. And then they realize, well, this is really an average value problem, so I've got to multiply that by 1 divided by 5 minus 2. Well, those two expressions in that red box are not equal. And a student cannot connect expressions with equal signs if they aren't equal. And even though this student produced the correct answer at the bottom, 39 divided by 2, they would not get full credit for this answer. So they can't link expressions with equal signs that aren't equal. And finally, here are just a few more AP Calculus exam tips for your students. Look, don't forget to show all of your work. I already mentioned this phrase once, bald answers. Bald answers rarely get full credit. Students should be succinct as possible, but certainly show their logic and demonstrate their solution technique. I want to remind you to have your students not to round intermediate results. So most commonly, students might have to find a point of intersection. Remember that they need to say that x and maybe that y value to the greatest degree of accuracy allowed by their calculator, by their technology, it is certainly acceptable and recommended that they create a variable. Call that intermediate value something like A, and write down 3 or 4 digits to the right of the decimal for A on their paper, but store that to the greatest degree of accuracy in their calculator. And then, of course, they can use A in any calculation on that page. Remind your students not to give up if they can't solve part A. Yes, you're absolutely right. Certainly, sometimes the answer in B depends upon what you did in part A and so forth. But if you can't solve one of the parts, don't give up. Try the remaining parts. Don't waste time erasing bad solutions. Look, we all know that sometimes students make an attempt at a problem and then realize, hey, wait a minute, that's not the way it's solved. I've got to do it a different way. Just have them quickly cross it out with an X and move on. They don't have to worry about erasing anything. Anything that's crossed out is not read. Make sure that your students answer the question. Look, the final answer doesn't have to be double boxed or anything or with arrows pointing to it. But make sure that they do indeed answer the question. Make sure that your students don't say too much. You know, sometimes students get a final answer and then they think, well, you know, I know an awful lot about this question. I'm going to tell these readers, these graders some more. They shouldn't do that. Because sometimes if they go on to say too much, and if they say something incorrect, they could lose some points. Now, not in my class in number 7, but on a high-stakes exam like this one, don't simplify a numerical answer. Remember that a final numerical answer does not have to be simplified on the AP Calculus exam. And remember that now the AP Calculus exam is rights-only scoring. So that means on the multiple choice portion of the exam, a student does not get any points off for an incorrect answer. So it doesn't hurt the student to take a good educated guess. Okay, so Mike, there's some of my tips. I hope that helps a little bit. And I'm going to try to, if I can, pass this over to Tom.
Okay.
There we go.
Thanks so much, Steve.
And I'll share my screen. Okay. And let's see, is that showing up okay?
Yes.
Looks
okay.
good.
Yep. And I'm going to be driving some technology. I've got TI-Nspire and TI-84 SmartView available, and Vicki's going to take us through some examples. I'll drive as best as I can on the technology.
All right, let's go to the TI-Nspire first.
Okay.
So we thought we'd go over area volume question or two that would be similar to something the students might experience on the exam. This would also cover some of the things that Steve talked about, storing intermediate values, storing functions, and making sure you wrote your expressions correctly. So Tom has stored some functions for us. We have f of x as that rational expression, 12 over 1 plus x squared, of course, then minus 1. We have g of x, 4 sine of x over 3, and we have h of x, which is a quadratic x squared minus 3x minus 3. So let's start with the first function, f of x, and suppose you had an AP question that read, let R be the region enclosed by the graph of f of x equals the expression that you see there, and the x-axis. Find the area of the region. So what the student would probably want to do, whether a graph is presented on the exam or not, is to graph that function. So Tom, let's graph f of x.
Okay. I'm going to go to a graphs page, and because of defined f of x already, we can actually use that name. So I'm going to do get our graph there, and I'll just refer to it as f of x.
Okay. And we had a problem like this on an exam a number of years ago, and students were a little bit confused about the graph that they were actually observing because they looked at the graph on sort of the standard window. So one of the skills or tools that you need to be able to use for the AP exam is to graph a function in an arbitrary window. And perhaps the window you're looking at is not the best window that you would want to observe. So let's notice that this function actually has a relative or an absolute max that's a little larger than 6.667. So let's change our Y max to something like 15. And we can do this through the menu, or we could actually click on the Y max on the screen. So students have preferences of what they like to do, and I would think at this point in their course of using TI technology, they've kind of adopted their favorite. So let's go to Windows Settings and change our Y max to 15. Now we won't have a proportional window anymore, but that's okay. Thank you, Tom. So you can see that we didn't have vertical asymptotes here, as some students thought when this similar question was on the exam a number of years ago. We have a nice, smooth, continuous curve, and what we now want to do is find the area enclosed by that curve, f of x, and the x-axis, which means we need to know the x-intercepts. And so if you happen to notice that this curve is symmetric with the y-axis, we only need to find one x-intercept, and let's find the one on the positive part of the x-axis. So we could go to Menu and Analyze Graph and 0. And so it asks us for a lower bound, so Tom's going to move his cursor over close to that x-intercept, and there we have 0 showing up. So one of the things I want you to notice is that it's only reporting 2 decimal places, but the calculator actually is storing many, many more decimal places. So let's actually store that value. And this is definitely a skill that students need to have if they're using the TI-Nspire on the exam. So Tom, if you would hover over our x-coordinate there, 3.332, and let's press the variables key. And store variables. And let's pick A. And press Enter. And notice that the numbers are bold now. That means it is stored. So Tom, if you could add a calculator page.
Okay.
And let's just type A and enter. And you will see that we now have more decimals reported by the calculator. So if you were doing this as a free response question, I'd highly recommend that on your paper in the space for this problem, you actually write A equals and report at least 3 decimal places as you record it on your paper. So I would record 3.317 if I were rounding, or 3.316 if I were truncating. Okay, so we've got our 0. So let's now find the area. So we need to pull up our definite integral template, and we can either do this through our menu with calculus, or we can use our template button. Tom is on the template button, so let's use that. Okay, so it's in the 3rd row, second one over, as we're calculating a definite integral. We press Enter. And so we need our lower limit to be negative A and our upper limit to be positive A, and our function is f of x. And we need with respect to x. And we should now have our area. So on the exam, you would need to write your definite integral from negative A to A, because you've already recorded a value for A that you've stored on your paper, and then if you were to write the definite integral from negative A to A of f of x dx equals 24.037. Tom, let's go up and highlight that 24.0376 right quick and press enter. And so sometimes I just like to look at more digits because I want to make sure that I'm recording the correct answer. So 24.037 would be the truncated answer. 24.038 would be the rounded answer. I honestly tell my students to truncate so that they don't make a silly mistake in rounding, and that's usually a very safe way to report their answers on the exam as long as they report 3 decimal places. Okay, so let's suppose that we were going to take that same region and rotate it about the x-axis, and now we want to calculate the volume. So let's go back and look at the graph just a second. And if we can imagine rotating about the x-axis, this is going to be a disk problem. And so, Tom, if we go back to our calculator page. Okay, so just press enter. There we go. So let's get our pi because we need to do our pi times the definite integral from negative A to A.
Okay.
And we'll go back to our template, and it's still highlighted, so that makes it nice. So negative A to A. And now we need to open a parenthesis and f of x. And one of the things that I've noticed is that students sometimes are a little bit careless about where they put their squared. So you need to make sure you're squaring the function and not the x. So we would need to put our squared here. And then with respect to x. And we should have our volume. So are there any questions that we need to deal with, Mike or Steve, that you've noticed? Okay.
I don't think so, Vicki.
Okay. All right. Sounds good. Okay. So, Tom, can we switch over to the TI-84 and kind of let's go through the same problem so that those who use the 84 can sort of see something similar? So Tom already has our functions entered in Y1, Y2, Y3. We'll get to Y2 and Y3 in just a moment. I want you to notice in Y1 the parentheses around the 1 plus x squared, so students need to be very careful about how they enter that expression. Okay, so let's only graph our Y1, and you've got it, the equal sign highlighted, so we'll be in good shape there. Okay, it happens that this window shows a little bit more of the graph as far as the Y max, so students probably can visualize that they can see that absolute max there, so that's okay. Let's go through the strategy of finding our x-intercept. So let's do second, calculate, and we want a 0, which is number 2. And it asks us for a left bound, and a little cursor should show up here. There he is. Okay, so we want to be to the left of our x-intercept, and enter, and then a right bound. Okay, we're a little past it now. Enter, and then it says guess. I usually try to move close to the x-intercept. You don't have to be on it. You just need to be close to it, and press enter. Okay, now, Tom, let's press enter, and let's go to a calculator screen. So we need to quit our graph there.
Oops.
Oh, we have some interesting things there.
All right.
Okay, so let's press the, we can just go to store if we want to, or excuse me, we need to press X. And then store, and let's store it as A, so we'd need to press alpha, and the math key is A, and press enter, and you'll notice that that's the same value that we used on the TI-Nspire that we have stored. Now we need to calculate our definite integrals, so we will go to our math and our number 9, function integrate. And we have a nice, pretty print integral here, so we'll go through the same procedure. We need -a. You have to remember to press your alpha button to get your A, and then A. And then our function was y1. So we go to variables, y variables, function, number 1. And then we need our dx. And press enter. And we should have the same value that we had when we worked with the TI-Nspire, and we do. The only thing that would be different about doing our volume problem would be including your pi and your square of your f of your y1 in this case. So I don't believe that we're going to need to do that. So Tom, let's go back to the TI-Nspire.
Okay. Tom, before you do that,
okay.
I just wanted to see if we could answer one question here. Can you just go back, if you could, Tom, to the y equals screen?
Sure. Here we go.
Very good. I just wanted to see that y1 again. There was a good question here, I think, about taking that same region, let's say the region in the first quadrant, bounded by the graph of y1, the x-axis and the y-axis, taking that region and revolving about the y-axis or even about the line x equal a. Now, as I thought about that real quickly, I would think about doing that by using cylindrical shells, I guess, would be the easier way to do that. But that's not tested on the AP Calculus exam. And Vicki or Tom, if you want to add anything to that, I'm just looking at that y1 kind of quickly. I might be able to turn around and solve that for x explicitly in terms of y. But we would not ask a problem where a student was forced to solve or find a volume problem using cylindrical shells.
That is correct. I really think that that particular problem would be much easier with shells, and so I'd hate to try to go through the algebraic manipulations that we would need to do to be able to do it as a disk with the cross sections perpendicular to the y-axis. It would take a good bit of math and algebra.
Good.
But
thanks,
sure. I'd also add, though, that if a student used cylindrical shells, even though that's not part of the course description, it's a perfectly valid method, and they would, as long as they did it correctly, they would receive full credit if they used that method and it was appropriate. Yeah.
Yes, that is correct.
Okay.
All right. Well, I said we go to the Nspire. I guess we could just stay right here on the. It doesn't make any difference. No, it doesn't matter. We can stay on the 84. We can go. All right. You're on the Nspire. That's fine. Okay. So let's look at the graph of our other two functions.
Okay. So I'm going to go back to the graph.
Okay.
Actually, just pull up the graph entry line.
Okay.
And I'm going to change F1 to g of x. That was the function that was defined on the previous page. I'll just go back there real quickly so you can see. So here's our g of x and h of x. We're going to graph both of those. So F2, we'll put in h of x. And then we should get, whoops, I guess I didn't get my first one in there. So let me try to recover there. Oh, there we go.
Yes, somehow it didn't
change. That's the g of x. I think when I went back to the other page, that happened.
Oh, okay.
There we go. There's the two graphs we wanted.
Very good. Okay, now we need intersection points with this. So there are actually two techniques. One is the menu that we were on a few minutes ago where we found the 0. But let's look at something else because I actually try to encourage my students to use this to save time. So let's go to menu. Let's go to geometry and points and lines and intersection points. And the advantage of this is that it will find both intersection points at the same time. So notice there aren't any prompts. So what you have to know or understand is that you need to click on the two graphs. So we'll press enter when we're on the graph of the first function, and then enter when we're on the graph of the second function, and both of our intersection points show up. If you were to go to the menu, Analyze Graph, Intersection Point, you'd actually have to go through the procedure for each one. So this just saves a little bit of time. Okay, we would want to store these. So let's click on the first one, and then Variables, and Store Variable. And let's go with B this time, I guess, since we've already used A. And then we'll do the same thing with the x-coordinate of the second one. And let's call this one C.
C, okay.
Okay, so we have B and C. Okay, now the other thing is if I wanted to, well, I think I had maybe finding this would be the region of a solid. This region would be the base of a solid where cross-sections are squares. So let's go through that problem. One of the things that I need to notice about this region is that I'm going to call it the blue graph, which is G of X, has higher Y values than the red graph, which is H of X. My students, in class, we call this the top curve and the bottom curve, or the upper curve and the lower curve. So when we want to find the volume of a solid where this region would have cross-sections that are squares that are perpendicular to the x-axis, then we would need to have our f of x minus, our g of x minus our h of x, or our f1 of x minus our f2 of x. So if we could, let's open let's go, I guess we can go to the same calculator page we already had. We'll be fine.
Sure.
Okay, so now if we're going to do cross sections, we need our definite integral, and we need B as our lower limit, C as our upper limit. Okay, and then this is where students really need to understand that storing those function names, either the H and the G or the F1 and the F2, and it doesn't matter which, is so important. Because if they try to retype the functions and that second function is the quadratic, they may forget to distribute the negative sign. So it's just real important to use function names here. So G of X minus H of X. And I would report the exact same thing on their paper when they're writing their definite integral. So they need to record their B value, their C value, then write this integral exactly as Tom has just put it on the calculator screen with respect to X. Notice this is also in reference to something that Steve brought up. We're not doing a washer problem. We're doing a cross-section where the cross-section is perpendicular to the x-axis or squares. So we do need a G minus H, that whole quantity squared. So if we'll press Enter, Tom, and we have our volume. And we could record 152.972, and that would be a rounded or truncated answer. So I guess we need to kind of look at the same thing and make sure that we can find those intersection points with the TI-84.
Okay. So I'll go to the Y equals menu and turn off the Y1 and activate Y2. Y3, where I'd already entered those two functions that we were talking about.
Great.
And let's see. We'll just graph these in the window we had before. Oh, it's not bad. Okay.
Yeah, that looks pretty good. Okay, so let's find one of the intersection points. I'm kind of looking at our time, so let's at least go through one of them. So we would go to our calculate second trace, and then we want an intersection, which is number 5, and it doesn't matter which one we do. So let's see, first curve, I guess we just need to press enter. Second curve, it jumped to the second one, so we can press enter, and then a guess. I did notice that someone had put something on the Q&A a little while ago that they usually leave their cursor at the second one, which is usually fine. I just like to feel like I'm a little closer to the intersection point when I use this particular feature. So there's our intersection point, and that is correct. And if you remember the procedure that we went through a few minutes ago about storing that value, we would do the same thing here, and we'd be in good shape. So X stored to, I guess we'll use our B again. And there we go. And we would do the same thing with the other point of intersection.
And I'll just throw in here that while you did both intersection points on the Nspire, here we would need to do this sequentially because it's only going to have that last value of X.
Correct. So you wouldn't want to find both of them and then do the little store thing. So you would need to do one intersection point, store that value, then the other intersection point, store that value.
Yeah. I'll just run through that again.
Okay.
So we found that second intersection point, and then we can go store that in C. Okay.
Okay. And then we could do our definite integral again,
okay.
B to C.
Okay. And let's see, so we'll do math. Okay.
So students really need to learn how to access their, or how to store values and access the alphabetic letters that they've stored these values as, so that they can pull up their upper and lower limits. And then we've got Y2 as our upper curve minus Y1. And again, please do not type the functions back in again. So you've graphed them, so they're stored for you. Use their names on the calculator.
And on the 84, I actually had these in Y2 and Y3, so that's why I'm getting those like that. And then, whoops.
Tom, while you're typing that, if I could just answer two quick questions that I saw.
Okay.
If that's okay.
Yeah.
So one of the questions was, in this problem specifically, Vicki, is why don't you need a pi out in front of the definite integral here? And of course, I should probably add this to my frequently asked questions list. You know, many students believed that in any volume problem, you have to have a pi out in front or a square root of 3/2 out in front. And of course, this is an example, a great example of a general volume problem where we're integrating that cross-sectional area. And in this particular problem, that cross-sectional area does not have a pi in it, as it would say for disks. So no, there's no pi necessary here, and it's not necessary in every volume problem.
Although we do see them often.
and we do see them often, that's correct, that's correct. And the other question, which I thought was a really good one, is in setting up this integral, Tom, that you have on the screen, what if a student had written this as y3 minus y2 quantity squared? Well, that's actually correct. I mean, in my class, I might not like that because it demonstrates maybe that the student doesn't really understand what the upper function or the high function is and the low function, but that would actually be correct on the exam and of course would lead to the correct answer.
Because we're squaring, yeah.
Because we're squaring, exactly.
Yes, because we're squaring.
Yep. Thanks,
All
guys.
right. So, I'm not sure we've addressed all the questions. I see some new ones popping up here, but
probably about time to turn it back over to Mike. So, okay, so let me pass. on to, oh, let's see.
Hey, Tom, as you go through the stop sharing and give control back to me, Steve, I was wondering if you would chime in. We got a lot of questions earlier about the not need, if you will, for simplifying answers. Can you just elaborate that just a little bit more as far as how that goes?
Yeah, great question. Look, final numerical answers do not need to be simplified. What does that mean? Any numerical answer that you get, that your final answer, you don't have to worry about simplifying. For example, even if it's something like 0 cubed over 3 plus the sine of 0 plus e to the 0 plus 1. Look, you don't need to simplify that. And if students go on to simplify that and make a mistake, unfortunately, they would probably lose a point. So under the pressure of a high-stakes exam, a final numerical answer like that doesn't need to be simplified.
So one of the things I say, Steve, in class is arithmetic does not need to be simplified. And that usually helps the students.
Yep, very good way to describe it, Vic. Yeah, thanks.
And if I could just piggyback on that as well, the only thing I add to that, and I tell my students, is the only real reason to go through and fully evaluate and simplify that answer would be if that answer is going to be used at a later part, like part B or C or D. Sometimes it's really helpful to have one clean answer as opposed to an unsimplified answer. But otherwise, I agree.
Very good.
Okay.
So I do want to show one thing that was mentioned by Tom during the introduction was some of the resources that are available for our calculus teachers and students. And that would be on our website, education.ti.com. And if you hover over the Resources tab, there's a new tab that says TI in Focus, AP Calculus. And whenever you click on that, I love what Tom and Steve have created. And I think, Vicki, you were involved in this as well. You can select certain topics. So, for instance, let's say that right now you're getting ready to teach your students differential equations. Right now, the only year that is currently available is 2017, but once we have the 2018 exam, I'm told that there'll be some additional information forthcoming as the years roll on. But you can click on this and see all the free information that's available for you and your students. And I've used this in my students, and I can tell you that I'm a big fan. It's changed so far how I've taught my students certain things this year, and the perspective that Tom and Steve have taken, I think for me at least, is a little bit of a fresh look on some concepts that I probably could be teaching better. So thanks so much, Tom and Steve, for putting these together, and Vicki for reviewing them, and TI for making them available for free.
Yes, I think it's a great resource. I encourage everybody to go look at that site on the education.ti.com web pages.
So if you like tonight's format and you're looking for some additional professional development this summer, we're offering many professional development opportunities, and these development opportunities can be specific to a certain technology, say the TI-Nspire or the TI-Nspire, or certain content areas such as calculus. So please feel free to visit our website to learn more about what we're offering and where we're offering it. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope you share your thoughts in the post-webinar survey. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents that were used tonight by Steve, Tom, and Vicki. And if for some reason these links aren't working for you tonight, don't worry, you'll automatically get a follow-up email. And that follow-up email will be a link to the recording, a link to the certificate, as well as a link to the documents. If you're watching this on demand, go ahead and just copy that link into your favorite browser to receive your certificate. If you have any further questions after the webinar ends, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. Thanks so much, Vicki, Tom, and Steve, for everything you shared tonight. I think we had a lot of teachers and students on tonight, which is always exciting to see. So thanks so much, everyone, for joining us. And again, Steve, Tom, and Vicki, thanks so much for everything you shared.
Yeah. Thank you.
Our pleasure. Thanks,
Thank
Mike.
you.
And we hope to see everyone back online real soon. Have a great night.